Welcome to this walkthrough or demonstration of one of the exercises we have in relation to the lecture on moisture transfer in pores. One of the themes of that lecture is to have a kind of simplified representation of a building material and the porous structure of such a material, where we assume that we can make an analogy with a set of pores, each of equal size or radius, but varying such that altogether the whole volume of pores in the material are represented by only a certain number of such pores. So we have a bundle of such pores, so it's a bundle of tube analogy to a building material. The whole porosity of our building material that we have for this exercise is 25%, and that also means that we have a density for this kind of material which is 660 kilograms per cubic meter. And then we have the fraction out of those 25%, but out of that, how much do each of them represent? It's made such that these numbers here, those fractions, they add up to 100%. So how much they represent each out of the 25. But we're going to, with this exercise, to calculate two types of curves. And one is the suction curve, or what we can also call the moisture retention curve, that tells us the relationship between moisture content, kilograms per kilogram, as a function of the capillary pressure in the material. And normally it goes over very much large ranges, so therefore we plot it normally where it's logarithmic to the capillary pressure. And the other curve we'll show is the sorption isotherm, which is again the moisture content, but as a function of the relative humidity. This links to the lecture on moisture in pores. And one of the slides we have there, we use only the lower half, which talks about the Kelvin equation. That's where we will end up. We have some pores here. They have two different sizes here. We know that because of the surface tension, which draws up the liquid, that we have an under pressure. So we have low liquid pressures here. And then the density of water vapor molecules depends on the thermal equilibrium between the air, the volume of up here in the air with the vapor, and then the under pressure in the liquid below here. And it is such that the smaller the pore, the more we have the reduction of the vapor pressure over here. So the density of water vapor molecules should be seen to be less here compared to there. If we have a completely flat surface, water surface, well then we have the normal saturation vapor pressure over such a water surface. But as we have curved, then the saturation vapor pressure is lower and lower the smaller we have the size of the radius. That comes from the first equation here. So PV saturation star means for this condition here, for such a curved meniscus, what is the vapor pressure at saturation over that? Because that becomes what we call the vapor pressure normally under such condition. The star indicates it's for one pore under its condition. And then we have from the equation how it has a relationship to the surface tension of water, the contact angle, which we normally assume such that the cosine is 1 if we know nothing better. And then, most importantly, we have the radius down in the denominator here, density of water, the gas constant for water vapor, and the absolute temperature also here. So then we can calculate those relationships. But interesting is also the Kelvin equation that tells us, based on that vapor pressure we found from before, when we insert that, divide by the normal saturation vapor pressure, then we calculate what is our relative humidity in that air over our curved water surface. How it relates to that capillary pressure we had down in the liquid part of our pore. So now we can make that calculation between relative humidity or capillary pressure. Again, some other properties that we know. So the rest, I will just go into the spreadsheet, which is the suggested solution to the exercise. So again, some repetition, a little bit of the formulas. Now put in such a form that we can isolate directly the capillary pressure by combining the two equations from the slide I showed before. So we can calculate the capillary pressure based on those geometrical figures here, and using again the value for the surface tension. And then as we just showed before, once we have the capillary pressure, then we can also calculate the relative humidity. And this we now do, that's what it says here in the text, for all those radius sizes we have in our model material, you could say. Again, some values that we have from the exercise for density, and the value which is set here it is if all the pores are filled with water, so if the material is saturated, then based on this information here, the density of the material, then we can calculate what is the moisture content at saturation. So 0.379 or 37.9%, that's the maximum possible moisture content when the moisture in the material is completely filled, you could say. The material is full with moisture. Down here in the calculation, we have the different pore size radii that we talked about. And if I just take it as an example, the smallest of the pore, the one that filled 2% of our material, that's with a very small radius, so 5 times 10 to the power minus 10, so 5 ångström, very small pores. If only that pore is filled with water, then according to the equations from before, well, then we can find the capillary pressure from that. So that was 2 times the surface tension that I talked about, and divided by the pore radius. So that was the first equation on the slide here from before. So that gives us the capillary pressure if only that pore was filled. So we want to plot it later on versus the logarithmic to that pressure, so we calculate that. And as I said, we can translate from capillary pressure to relative humidity. So the next column is in preparation of that, a calculation of that capillary pressure using the Kelvin equation as we showed it before. Well, if only that pore is filled with moisture, that was 2% of the pore volume of the material. So that means that it's 2% of the saturation value. So the moisture content for only filling that one would be 0.008 kilograms per kilo. So that is what we have in these formulas here. So the U double star here is if only that kind of pore size is filled, or only that kind, and so forth. But then in reality, the smallest pores fill up first. So when the next one is filled, then the previous one the smaller one has been filled already. So by adding them up, that's what we do here in the last column, then we get what becomes the total moisture content in the material as the smallest, and then the bigger and bigger pores are being filled. That's what we have here. So here are all our solutions, indeed, for these bundles that we have considered here for this material. And of course, they should all add up to 100%. So when we consider that distribution, now we can plot it. So to plot the suction curve would mean to plot the moisture content as a function of the, we take the logarithmic to the capillary pressure. That was our suction curve. And the other curve, that would be plotting again the moisture content versus the relative humidity. So all what's left here in the spreadsheet is just to show the results. So the moisture retention curve or suction curve comes here, and so that's on a logarithmic scale. And here is the dry region, so very high suction pressures, capillary pressures, or very negative, if you will, so low moisture contents. And here the material is wet and saturated, and the capillary pressures are by order of magnitude small. So that's where we have 100% relative humidity, but that is normally what we plot on the absorption curve with the same information, but plotted versus relative humidity. Comes here. Ta-da. So on a scale from 0% relative humidity up to the humid range here, 100% relative humidity, we plot the same values. So that was the story about bundle of tubes, capillary pressures, relative humidities, as we plot them in suction curves and in absorption curves.